Okay, so today is the first day that we're really going past what you learned in geometry class and SOHCAHTOA, besides the whole inverse trig function stuff. But today we're going to extend this to the whole circle and imagine if we went around the whole circle. So step one is I think we need to get better with our radians measure so that we're not always converting to degrees, right? I know that's what we all do. You convert to degrees and then you go back to radians, right? That's no fun. So I wanted to show you some important angles. The 45, 45, 90 and the 30, 60, 90 triangle are special triangles. Let's look at those increments on a circle if we went all the way around. So let's label what we know. We know this is 0, and this is how many radians? Pi radians. So what's up here at 90 degrees? Half of pi is pi halves. And if this is pi, and this is half of a pi, what's down here? Yeah, 1.5 pi, or 3 pi halves, because we like to write them as fractions. And if you haven't been writing them as fractions, you want to write it as a fraction as much as you can. Fractions, that's the way we write radians, way better than decimals, so try to get the idea of doing that. We want to break this up into increments of 45 degrees, because 45, 45, 90 triangle, but let me show you a great way to do this. If 0 to pi halves is here, what would be the measure halfway in between 0, 45 degrees, or what would be halfway between 0 and pi half radians? Pi fourths, which is why pi fourths is 45 degrees, because it's half of 90 degrees, or half of pi halves. You with me so far? So what if we broke this up into these equal parts? Like what if I went ahead and drew this halfway over here, sort of halfway? So think about it, from 0 to pi, I've just broken this into 4 equal pieces, yes? So how many pi fourths, how much is here? Like if I remember back in like grade school when you like shade in, you're like, if this is one whole, if I shade in these 3, how many is it? 3 pi fourths, right? Like it's 3/4 of the whole, so we say this is 3 pi fourths. And you can just count by fourths. 1 pi fourth, 2 pi fourths, 3 pi fourths. This would be 4 pi fourths, or 1, right? So what if I broke these into equal pieces also? What would be one more fourth than 1 whole pi? This is 4 pi fourths. Does it make sense that this is 5 pi fourths? Or 1 1/4 pi? I'm telling you, if you don't know fractions, you're going to learn them after doing radians. And if this is 5 pi fourths, is 3 pi halves the same as 6 pi fourths? Reduce it, so what would this be? 7 pi fourths. And what would 1 more fourth make? And what is 8 pi fourths the same as? 2 pi. So if you break this into fourths, it's the same as breaking it into increments of 45 degrees. And so these are special angles that we're going to spend a lot of time on. You can always do the conversion, but I hope that it kind of makes sense where these values come from and how you can think about them. And you could go through, I know my radians better than I know my degrees, because what degree is this? I'd have to think, and I'd be like, well, that's 270 plus 45, and then I have to add it up because I don't know it. But I know it's 7 pi fourths because I use radians more than degrees. So hopefully someday you'll get there. Our other special triangle is a 30, 60, 90 triangle. So the other one I want to talk about is what if we broke this up into increments of 30 degrees, like 30, 60, 90, 120, 150, 180. Those are also our special angles. So if from here to here is pi halves, this is pi, this is 3 pi halves. If I wanted to break quadrant 1 up into 30-degree increments, you agree that you kind of break it up like 30 degrees, 60 degrees. So it's like 3 equal pieces. Go ahead and do that on the other side too. Like try to break that quadrant up into roughly 3 equal pieces. Close enough. So I have 1, 2, 3, 4, 5, 6 pieces from 0 to pi. You with me on that? So how much is this? 1/6 of pi, or pi over 6. And that's why pi over 6 is 30 degrees, because it's 1/6 of that little chunk. How much would the next notch be? Yeah, or 2/6 is the same as 1/3, or pi thirds, which is why pi thirds and pi sixths have been our 2 special angles 30 degrees, 60 degrees. And we can really just count by sixths all the way around, right? Do you agree that this is 1, 2, 3 pi sixths? Is that the same as 1/2? So what does this become? 4 pi sixths, can you reduce that? 2 pi thirds, right? We want to reduce our fractions. But you can always think of 6, you just have to reduce. So if this is 4 pi sixths, what's this? 5 pi sixths. And I think of that, and hopefully soon you'll start thinking about that. 5 pi sixths is just 1/6 away from 1 whole pi, and that would be 6 pi over 6. So hopefully you can start thinking about that and where they would be on the circle as opposed to always converting to degree measure. Let's break this up into 6 equal parts down here as well. Roughly speaking. I should have used like straight lines so they would look better, but that's okay. Normally I don't print these notes off, so you had to make the whole circle yourself, so you know, just happy I gave you a circle to start with. If this is 1 whole pi, or 6 pi over 6, what's 1 more sixth than that? 7 pi over 6, or 1 and 1/6. I know, right? 7 pi over 6, what would this be? 4 pi thirds, because that would be 8 pi over 6. 9 pi over 6 is 3 pi halves, so this would be 10 pi sixths, or 5 pi thirds. And then 1 notch away from 2 pi would be how many sixths? 11 pi sixths, and that should make sense because 12 pi sixths is 2 pi. You don't have to have this memorized today, but at some point you're going to want to be able to know these without having to convert every time, because these are going to be the angles that we use over and over and over again. So 30, 60, 90, 45, 45, 90, you could get all of these angles using multiples of that. Okay, so does that help a little bit maybe with all these radian measures I throw at you? At least gives you something to look at, and again, we'll touch on this more. So what are we doing today? We're extending trig. We're going to talk about, instead of talking about these cute little triangles all the time, we're going to say, what if I graphed a point on the xy plane anywhere? How could I find all these trig functions of it? So they say, let theta be an angle in standard position with xy being a point on the terminal ray of theta, and we'll talk about r in a minute. So let's just draw an angle in quadrant 1, because that's what we're most used to. So I'm just going to draw my initial ray, and I'm just going to draw my terminal ray out here. And it says, let theta be or let xy be a point on the terminal ray. So just make a dot out here, and make a point xy. Up until this point in trig, everything you've done with SOHCAHTOA, sine, cosine, tangent, has always been in quadrant 1. We haven't really said that, but everything we've done has been in a 30, 60, 90, a 45, 45, 90, or in some other triangle that you could draw in quadrant 1. Today we're going to extend it and say this could be a point over here, this could be a point down here, this could be a point over here. No matter where you draw it, do you agree that if you took your point and you drew a straight line down, will that always make a triangle? This will always be your theta coming from like the two rays together. And if you draw the picture, you can still do SOHCAHTOA, but what we want to do is start thinking about it in terms of x's and y's instead of opposites and hypotenuse, because you might not want to graph it every time. So let's think a little bit about the side links here. This, normally we would say this is the opposite side, but in terms of your graph, how tall will this side always be of your triangle? It will always be whatever y is. Agree with that statement? So the opposite side kind of becomes y. And how long will this part of your triangle always be? However far you are on the x-axis, which means yes, it could be negative, because what if your triangle was over here and x was negative? You can have a negative value here, which is kind of the new part. And then this is still the hypotenuse, but because we're thinking about this circle, we're going to call this the radius of the circle instead of the hypotenuse. So we're going to call this r. And they tell us this definition, that r equals the square root of x squared plus y squared. Where's that equation coming from? this some version of Pythagorean theorem? Could I say r squared equals x squared plus y squared? And all they've done is solve for r. So they just took the square root. If you still use this, that's okay. But usually we know x and y and we don't know r. So they just went ahead and solved that. So just know this is no new equation. It's just Pythagorean theorem solved for the hypotenuse. Okay? So instead of writing out sine as opposite over hypotenuse, I want to write it out using x's and y's and r's, which makes things a lot easier when we're doing this without a picture. So I can say that the sine of this angle is still opposite over hypotenuse, but using this picture, it will always be the y coordinate over whatever r happens to be. And we'll do one in a minute, and I'll show you how you can do it without graphing it. Cosine is still the adjacent over the hypotenuse, and if you draw a picture, you can do adjacent over hypotenuse, but it will always be the x-coordinate over your radius. And the tangent is opposite over adjacent, or if you have points, that would be y over x. We do need to say where x cannot equal 0, because we do have some weird values sometimes. If the point was on one of the axes, and it was 0, then the tangent's undefined. So that's how you can get undefined trig functions. R can never be 0 because you're never going to have a point, like it's not an angle if it's at 0, 0, so that's why we don't say on sine and cosine. But all of these can be undefined as well. So cosecant would be r over y, because you just flip that over, but you need to say y can't equal 0. So if y equals 0, then your cosecant is undefined. There was a question on one of the homeworks. I don't know if we talked about it in the second hour, but I don't know if someone asked in here. It was like, it's number 69 on some homework, and it was multiple choice, and it said, like, which one of these is undefined or something. And it was like a 90-degree angle, because we hadn't talked about that yet, but that's how you can get an undefined answer, because these weird things happen. Secant is r over x, but we have to say where x can't equal 0, and cotangent is x over y, where y can't equal 0. So what can we do with this? The next problem, I only did sine, cosine, tangent because I kind of wanted to hurry it up, but I could ask you to find all 6 of these. And I just want to show you how you can do this without a picture, but then I'll show you how the picture can help you if you want to draw it. But instead of giving you a picture now or a triangle, they're going to give you a point. And they say, let negative 12, 5 be a point on the terminal ray of theta, find sine, cosine, tangent. And I could ask you to find cosecant, secant, and cotangent, but if you can do these 3, I trust you can do the other ones. But here's the thing. This is x, and this is y. Do you need to draw a triangle to find r? You could. If it helps, you can always draw a picture. But the idea is you don't have to, because you always know that these are going to be the legs of your triangle. So to find r, it's always going to be the square root of x squared plus y squared. Which means I can say that's the square root of 144 plus 25, or the square root of 169. I can say that the radius, or the hypotenuse, would be 13. I'm going to sketch the picture for you in just a second, just so you can see it. But the idea is, on your homework, you don't have to draw it if you don't want to, because you have to learn. You have your notes today, but eventually, you want to know that when you see sine, you can say, oh, sine is y over r, no picture needed. I know that the sine of this angle would be 5 over 13. And cosine is x over r. And this is where you get negative values here. The cosine of theta is going to be negative 12 over 13, because the x value is negative 12. I'm just going to draw this while you're doing tangent here. If this was negative 12 and this was 5, if I drew the point out there on my ray, this is kind of what my angle looks like. And that's definitely a negative value. We'll talk about this more tomorrow when we talk about where the triangle comes from. The only way you can get a triangle out of this is if you draw this line down, but it's still, this is a height of 5, this is a length, I know it's weird to think of a negative length, but that's a length of negative 12. So if the picture helps you, by all means draw the picture, but you don't have to draw it. Tangent is y over x, so I can say that that is 5 over negative 12. You just got to know the ratios. Questions about that? So on the next page here, the only really other thing that I'm doing today is talking about in which quadrants are which trig functions positive and negative. Again, so far, everything we have done has always been in the first quadrant, so everything's been positive. But I want you to see how we can use these ratios to figure out what's positive and what's negative. I'm never going to make you like regurgitate this thing that we're going to write out. It's just supposed to help you and help you think about what's happening here. So let's write sine, cosine, and tangent in each one of these. Quadrant 1, quadrant 2, I'm only writing these 3 because if we're talking about positive and negative, if tangent is positive, will cotangent always be positive? If sine is positive, cosecant will always be positive. Like whatever sine is, its reciprocal function would also be the same sign. It's just flip it around. So I'm only writing these 3, but it works for the reciprocals too. Because sine, cosine, and tangent now connect to x and y coordinates, all you have to do is think about what the x and y coordinates are in each quadrant. So in quadrant 1, do you agree if you had an ordered pair, the x is always positive and the y is always positive? So let me write this up here, just because I don't have it on here. We've just learned that sine is y over r, cosine is x over r, and tangent is y over x. So the reason that everything we've done so far has always been positive is because we've all been in quadrant 1. And if these are positive, is r ever going to be negative? No, it's a square root. It can't be negative. So we're really just looking at x's and y's. So we can say in quadrant 1, they're all positive. It's the only quadrant they'll all be positive in. So think about in quadrant 2. First of all, what's the ordered pair? Is x positive or negative in quadrant 2? Negative, and y is? So think about sine. Sine is y. So in quadrant 2, is sine positive or negative? Sine is y. Y is positive. It has to be positive. Cosine is x. In quadrant 2, you agree that x is negative? So it's going to be negative. And what's tangent? If tangent is y over x, and one's positive and one's negative, what's tangent going to be in quadrant 2? Always negative. Again, you don't have to memorize this. You can just think about it, but I just wanted you to see maybe a pattern here a little bit. What about in quadrant 3? What's the ordered pair? Negative, negative, x is negative, and y is negative. So do you agree that sine and cosine are both going to be negative? Because y is negative, x is negative. What happens to tangent in quadrant 3? Because you get a negative over a negative? And then quadrant 4, you got to think about it sometimes, but I'm back over here on the positive side of the x-axis and the negative side of the y-axis. Yes? So sine is y, and y is negative, so in quadrant 4, sine is negative. Cosine is x, so cosine is positive. And tangent is negative. So you don't have, again, nothing to memorize, but do you notice that every trig function is positive twice and negative twice? Always. Like sine is positive in 1 and 2. Cosine is positive in 1 and 4. Tangent is positive in 1 and 3. So to memorize it, but just it's something to think about as we go through here. So the only other thing on your homework today, besides the point stuff that we just did, is there's some questions like this. And this is without a calculator, which means on your test, I'm going to give you these questions without a calculator. I can't stop you on your homework from using a calculator, but just know this would be on a test without a calculator. And it says, tell me whether it's going to be a positive or a negative answer. That's all I want to know. So think about 299 degrees. What quadrant is 299 degrees going to be in? Quadrant 4. Cosine is x. So in quadrant 4, is cosine positive or negative? Cosine is x. X is positive. Positive. You're definitely welcome to check with your calculator or check in the back of the book. And again, you can change this to degrees, but try to think of it at first without degrees maybe. 2 pi thirds. What quadrant is that going to be in? Quadrant 2, because it's not 1 whole pi, but it's more than 1/3 pi. It's over somewhere in here. So in quadrant 2, tangent is y over x. Is it going to be positive or negative? Negative, because one's positive and one's negative. And you can write the words positive or negative. But practice that without your calculator, because it's not going to help you on a test if you're using your calculator every time. Questions about that? I know that was kind of rushed, but it's like we're never going to have a full day of school again. So you're only doing 3 through 12 multiples of 3. Those are the point ones. And then I believe 17 through 20 are just what quadrant is it in. Or, I mean, is it positive or negative based on the quadrant. So that's not that much homework. Please start staying up on your homework. We're going to be adding new stuff every single day. And if you get behind, you're going to have a really hard time getting yourself out of that hole. So do your homework, Trevor. I am singling you out. I know you can do it. You just have to do it. I'll single a new person out tomorrow.
I think Thomas is the office, please. I need Thomas Fanning and Alexander the office. Thomas Fanning and Alexander the office.
I want to just he asked me to get dropped, and I said no. This class is better. What are you doing after school? Like after high school?